Hello guys, welcome back to part 2 of the Logarithms in One Shot. Okay, this is the first chapter which we are covering for the one shot series split into two parts. I have already uploaded the first part on the channel. Okay, this is the second part of it. If you've not watched the first part, I would suggest you can go watch the first part because all the concepts are carried forward over here. Okay, if you're very confident for the first part, like, oh, all easy stuff, I don't need to watch, I'll just watch the second part, then sure. Okay, if you are ever feeling stuck though at any point because of some concept which was covered in the first part, then I would highly recommend that you go back and watch the first part. Okay, so what's today's topics about? So here's the first topic, natural logarithms and their inverse. Now I'm sure all of you already have a good idea of this, and I in fact gave you a little bit of an idea of this in the first part as well. Now, you all remember pi, right? And we know it's approximately equal to 3.141 and then blah 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 blah. Okay? Let me introduce you to another constant, a new constant. It's called E. And E is approximately equal to 2.718 blah 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 blah. Now you'll be like, oh my god, one more constant, boring. Well, it is what it is. Okay, I can't do anything about that. But think about it this, okay? E is such a common number and is such a common exponent. Okay, for example, you'll have many exponential equations with e, like e to the power x, e to the power 2x. Okay, so if exponents are there, suppose like e to the power x is equal to 3, we will need logarithms with the base e, don't we? Log base e3. Now, I've already mentioned this earlier that e is such a common base that there's special notation for this, and we just write ln 3. So instead of writing log base e, we just write ln. Okay? And actually, you'll be surprised to know we call this the natural logarithm. Okay? ln, we call this a natural logarithm, or I'm too lazy to call it natural logarithm, I just call it ln. Okay? But the systematic name is natural logarithm. Now, if you're like me, you'll probably be wondering, what's so natural about this? Is it found in nature? Like, what's so natural about this? And what is E actually? What is E? Like, okay, pi I can accept. It's the ratio of the circumference and diameter. That's always pi. What's E actually? And what's so special that it's natural? Like, that's a really big statement, right? Calling this number which we have not even heard about and just hearing about this, which has some random value 2.718, and you just call E like A, B, C, D, E, and we are calling it natural, like, means there has to be some really big significance. And if there's not, then dude, what are we doing? Why are we calling this natural? Okay, so there are a lot of theories on this. Not theories, there are a lot of ways in which I can justify why it's called natural. Okay, and if you want, I can do another video on this. Okay, but I will give you one of the ways and a very quick and brief explanation on one of the ways why why you can say it's natural. Okay, suppose I take a graph of e to the x. We will learn how the graph looks like in detail later. Let me get the line proper. Okay, that's better. Nice, this is a good graph. Okay guys, respect the graph. It's beautiful. Okay, so this is like y is equal to e power x. Now we know from basic algebra and basic, knowledge about graphs that the gradient of this graph is not constant. Like how we have a straight line graph, the gradient is constant at every point. In this exponential graph, it's not constant. If you don't know that, I like saying it, take your pen and, okay, you should know this by now, that the gradient of this graph is not constant. Okay, but here's what's special about it. This graph is y is equal to e power x, right? Suppose I want to find the gradient at 2, at x equals to 2. All I have to do is just do m for gradient is equal to e power 2. If I want to find gradient at x equals to 3, all I have to do is m is equal to e power 3. So suppose I want to find gradient at any point at mx, it's a function, I'm treating a function for a gradient. It's just e power x. So the gradient of this graph at e to the power 100 at x equals to 100 is just e to the power 100. And this is the only graph, only function in the world where e power x is the graph and e power x is your mx. This is the only graph in the whole world, in the whole universe so far. Okay, if you come up with another graph like this, please share it with everyone. You will probably get a Nobel Prize for this. Okay, but so far this is the only graph which has a gradient function of itself. Okay, but we don't need to know all this. Okay, for some of you who were curious, I just want to explain it because it's better if this is explained, and many teachers just don't do it. Okay, now let's just get a bit more used to e. Okay, so e is actually essentially like natural logarithms is the same as any other logarithm. Okay, the same rules apply, nothing changes. You know, your argument should also be positive. Okay, your addition law, division law, okay, now let's look at a logarithmic equation. Okay, this is going to be a bit more detailed than all this simple stuff like hiya, all this is simple, ma. Just one step was your answer. Okay, now let's look at a logarithmic equation. If you're not sure what I'm talking about, go check the previous video. Okay, so here's how it goes: e to the power 2x minus 2e to the power x minus 24 is equal to 0. I suggest you pause the video and try it yourself. I will wait 2 seconds for you. 1, 2. Okay, assuming you have given it a go, what I'm going to do is I'm going to write e to the power, okay, sorry, I'm going to write, what I'm going to do is I'm going to take e to the power 2x and write it as e to the power x squared. This is just basic indices. Minus 24 is equal to 0. Now what I aim to do is convert this from an exponential equation to a quadratic equation. Oh, by the way, sorry, I said logarithmic equation just now. This is an exponential equation which we're solving. Okay, but I still covered it previously if you're not sure. So what I'm going to do is I'm going to choose s, okay? S is equal to e to the power x. So this just becomes s squared minus 2s minus 24 is equal to 0. Fifth standard factorization, s minus 6 and s plus 4 is equal to 0. Yes or no? S minus 6 and s plus 4 is equal to 0. Okay, we are lagging a bit. S minus 6 and s plus 4 is equal to 0. Now we know that because s minus 6 and s plus 4 is equal to 0, s is equal to 6 and s is equal to what? Negative 4, eh? I hope you got that. S equals to 6 and s equals to negative 4. Now some students very happily, this is my answer, this is my answer, but this is not your answer. Sorry dude, it's not your answer. S equals to 6 and s equals to negative 4 is not the answer, it's the value for s. But you want the value for x, dude. Now you'll be like, okay, I have s, how can I find x? Yeah, s is equal to e power x, ma. So, if 6 is equal to s and s is equal to e power x, means e power x is equal to 6 and e power x is equal to negative 4. So, x is equal to ln 6. Okay, that's equal to blah blah blah. You can find that in the calculator yourself, and x is equal to ln negative 4. Now if you leave this and you give this answer, you will get wrong, and if you leave this answer, I will personally come and punch you twice. Why? Because the argument cannot be negative, it cannot be 0. You remember from the last class, if you're not sure, just go to the channel, watch the part 1, okay? The argument has to be positive, okay? Please don't forget this, the argument has to be positive. Why that happens, okay? Why can't it be negative? Why can't it be 0? All of that has been already mentioned in the last class, okay? Essentially, this is just revision, and this is just an exponential equation. Nothing is new here. The only difference is it's in terms of e, okay? So ln 6 is your only answer. Okay, you can leave it ln 6, or you can find whatever the value of ln 6 will be in your calculator, but you cannot put ln negative 4 as your answer. In fact, you could try putting ln negative 4 in your calculator, it will give you error. Okay, so ln 6 is your answer. We looked at natural logarithms, we looked at e. Okay, now let's move on to the inverse of logarithmic functions. Now, inverse functions are quite a familiar concept with all of you. You've learned it when you were learning functions as a special chapter, but I am sure most of you have forgotten, so let's just do a recap, okay? Let's not take logarithmic functions, let's take a normal function. Suppose fx is equal to 2x plus 5. The basic idea is if we have to find the inverse, first thing we can take fx as y, because if you're plotting a graph, it's y against x, right? Not fx against x. Okay, so finding the inverse is in some way we are switching the variables. So what we're trying to do is, here y is the subject, we'll make x a subject, because that way we are reversing the subject, so we are reversing the function in a way. So that's kind of like the idea. So I'll do this very quickly. X is equal to y minus 5 divided by 2. But we know that inverse functions can only be in terms of, like, f inverse of x will be in terms of x, right? F inverse x won't be in terms of y. So f inverse x will just be equal to x minus 5 over 2. Okay, that's really simple. So we can extend this idea to logarithmic and exponential functions also. Okay, let's take an example. Suppose fx is equal to the e to the power x. If you have to find the inverse of this, I'll just write fx as y, which is equal to e to the power x. If I have to make x a subject, what will we do here? X is equal to ln y. right? We'll use ln because e is the exponent here, natural logarithms, and that means that f inverse x is equal to ln y, right? No, it'll be equal to ln x because inverse of x will need x in the function, right? You can't have f inverse x equals to ln y. That's a bit strange to have. Okay, so here's the relationship we have. That logarithm, that e to the power x, like I found the inverse of it, I got ln x. So does that mean that exponential and logarithmic, does that mean that they are inverse of each other? Inverse functions of each other? Let me write that weird arrow. Are they inverse functions of each other? Like, okay, one case is true. Is every case like that true? Well, yes. Okay, all exponential functions and logarithmic functions are inverse functions. And I hope you remember, inverse functions are a reflection across y is equal to x. Okay, if you don't quite remember your functions, then just remember that you have to swap the variables. Okay, so I make x a subject, so I get f inverse x equals to ln x. Inverse functions are reflection across y is equal to x. Domain of f is equal to range of f inverse, and blah 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 blah, and so on. Okay, everything same applies with here. Just how all the rules of logarithms apply with natural logarithms, all the rules of functions apply with inverse functions and functions of exponential and logarithmic functions. I mean, they are still functions, right? So let's take a more detailed example. E to the power x is quite simple, I would say. Okay, so suppose I have an fx, as I have the question right here, which is 4e to the power minus 3x. Let me write that down. 4e to the power minus 3x plus 5. Okay, your job is to find the inverse of this. Okay, pause the video and try again. Pause the video and try. Okay, I'll wait 1 second. Okay, I hope you paused the video and try. So here's the solution. Fx can be written as y, so y is equal to 4e to the power minus 3x plus 5. So 4e to the power minus 3x is equal to y minus 5. That means e to the power minus 3x is equal to y minus 5, the whole thing divided by 4. Now, if I have to make x a subject, I can't make x a subject directly, but I can make minus 3x a subject. So minus 3x will be equal to ln y minus 5 over 4. So that means x is equal to negative 1 over 3 ln y minus 5 over 4. But is that our inverse function? No, we are very close, but we just have to write it in terms of x. Okay, so our final solution would be f inverse of x is equal to negative 1 over 3 ln x minus 5 over 4. Okay, so that was one example on finding the inverse function, and we learned that logarithmic functions and inverse functions are inverses of each other, which means they're a reflection across y is equal to x when we draw the graph, which we will learn in more detail in the later section of the video. Now, before we move on to the last subchapter, which would be sketching the graphs of exponential and logarithmic functions, I want to cover one more question on the inverses of them, because I felt that the examples which we did, they were just pretty straightforward examples which had no, nothing much for you to think about. Okay, so here's one example. It's regarding composite functions and a bit of inverse functions also. Now, I hope you remember composite functions, but if you don't, let me just revise it for you. Suppose, let's go back to our favorite one, fx is equal to 2x plus 5. And if you have to find f3, it means you substitute 3 in the function. Okay, we just get 11. Now, if they are asking us fgx, it's the same thing. f3, we substitute 3 in the function. So fgx, it's like substituting gx inside fx. Okay, it's the same thing. Like f3, we substitute 3 in the function. So fgx, we substitute gx inside the function. Brilliant. Now let's actually solve this question. So do pause the video and give this a go, yeah? Until I'm erasing. After that, let's get into the solution. Erase. Okay. So I hope you've given this a shot. Let's do part A. So fgx, so means gx goes inside fx, okay? So that means you're finding f of what's going inside f, ln 2x plus 1, ln 2x plus 1. Okay, brilliant. So ln 2x plus 1 is essentially the x inside this. So that becomes e to the power 2x. And what is this x? This x is this thing over here. Yes or no? So e to the power ln 2x plus 1. Okay, of course we can simplify it a bit more. You can make it e to the power ln 2x plus 1 square, power law. Okay, then this e and ln can cancel, so you get 2x plus 1 square. That means that f g x, okay, you don't need to put the bracket here, I just put it for your understanding to show you that it's gx going inside fx. That is just equals to 2x plus 1 square. Okay, very good. Now part B, this is where it's a little bit interesting. Okay, let me just write the functions again. Okay, because I have to go down a bit. So fx was e to the power 2x and gx was ln 2x plus 1, and x is greater than -1/2. The domain is important. Okay, because there can be some cases we can accept some answers and reject some answers. The domain is important. Okay, so what's the question asking us? We have to solve fx is equal to 8g inverse of x. So let's find g inverse x first. Okay, I'm going to find g inverse x first. We can see this is a logarithmic function. So by our common knowledge, we should know that the inverse of it will be some exponential function. Okay, so it means gx is equal to ln 2x plus 1. So we have y is equal to ln 2x plus 1. How can I make x a subject here? Well, we know that means 2x plus 1 would be equal to e to the power y. 2x plus 1 would be equal to e to the power y, right? That means 2x is equal to e to the power y minus 1. X is equal to e. Okay, actually I'll just write it over here at the corner. I mean, not at the corner, at the side. So x is equal to e to the power y minus 1 divided by 2. So this isn't a final answer, this is just g inverse x. G inverse x is equal to e to the power x minus 1 divided by 2. Okay, that's g inverse x. Now let's solve the equation they want. Fx is equal to 8g inverse x. Okay, so I just, to show the functions, I will do it. Fx is e power 2x, so e to the power 2x is equal to 8. Okay, fx 8. G inverse x we just found. So 8 times, what is g inverse x? This thing over here, e to the power x minus 1 divided by 2. Okay, you have to solve for x in this. Very good. I hope every one of you got the same thing till here, because I assume you solved this on your own as well. So e power 2x, I'll just write this as 4, because 8 divided by 2 is 4. So 4 times e to the power x minus 1. So e to the power 2x is equal to 4 e to the power x minus 1. So e to the power 2x minus 4 e to the power x plus 1 is equal to 0. Okay, everyone following so far? I hope so. So simple, I'm just going to do s is equal to e to the power x square. This is just the same as e power x square minus 4 e power x plus 1 is equal to 0. Since s is equal to e power x square, by now we are pretty pro in this. S minus 4s plus 1 is equal to 0. Can this be factorized? I'll just use my calculator to check, because it was s square here, sorry. Let's just check if this can be factorized. I don't know. It doesn't, I just can't find direct factors. Yeah, it can't really be factorized, which means we need the quadratic formula. Okay, don't get scared, we know the quadratic formula. I was just checking with the calculator actually if it has direct roots. So s is equal to negative b. What's b? Negative 4. So negative of negative 4 plus minus square root b square. B is negative 4, so negative 4 square minus 4 times AC. A is 1, C is 1, divided by 2A, 2 over 1. Okay, too much black right now, so let's just change to red. So is equal to 4 plus minus square root of, this is 16, this is 4, 16 minus 4, 12 over 2, and root 12 can be written as 2 root 3, I believe, because it's root 4 times 3, and root 4 is just equal to 2, right? So we could write it as 2 root 3 plus minus 2 root 3 divided by 2, which is equal to 2 plus or minus root 3. This is our answer. No, this is not our answer, because this is the value for s. Okay, this is the value for s, not for x. What's s? S is equal to e power x. Remember over here, we defined it. Let me go back to the top where we defined it. S is equal to e power x squared. Over here. Okay, so, oh, I'm so sorry. S is not equal to e power x squared. S is equal to e power x. Okay, by now most of you have probably thought I've done some weird mistake. I'm sorry, s is equal to e power x. Okay, sorry about that. By now many of you would have probably just gone like, oh no, he's wrong, he's wrong. Yes, I'm sorry, that was just a stupid mistake on my part. You know, things happen. Okay, so e to the power x, it can either be 2 plus root 3, or e to the power x can be equal to 2 minus root 3. Okay, first of all, we need to check if 2 minus root 3 is positive. Okay, 2 minus root 3 is approximately 0.26, 0.27, same thing. So then we can actually solve this. So then on the left side, x is equal to ln 2 plus root 3. Okay, I'll just put that in the calculator. We should get ln 2 plus root 3. That's 1.32. Okay, and then on 1.32. Okay, and this one, x is equal to ln 2 minus root 3, which is equal to ln 2 minus root 3, negative 1.31. Okay, so we have two answers. No, don't fall in the trap every time. We don't have two answers. Huh? I found this legally. I haven't broken any law. So why are you saying that this one of them is wrong and one of them is correct? My dude, let's look at the domain of the question. Okay, wow, I've written quite curved. X has to be greater than negative 1 over 2. X is greater than negative 1 over 2, dude. Let's check our answer. So the domain is x is greater than negative 1 over 2. Okay, 1.32 is greater than negative 1 over 2. Correct. Okay, this is correct for sure. Negative 1.3. Are you saying negative 1.3 is greater than negative 1 over 2? No, right? So we reject this answer. Okay, please don't put this sign in the exam. You don't mark your own paper. Okay, so x is equal to 1.32 and x is not equal to negative 1.31. So we have just one answer in this case. Okay, so that was a question which required composite functions as well as some knowledge of inverse functions. Okay, you might also be required to know the fact that, you know, domain of f is range of f inverse. Okay, you might also need to know that, so practice a few questions on that too. Now let's move on to the last subchapter, which is the graphs of logarithmic and exponential functions. Okay, now let's go to graphing logarithmic and exponential equations. So let's start with exponential equations. Okay, let me start with y is equal to e to the power x. Okay, so we know the drill. Okay, what are the two things you always need to find in when drawing a graph? Well, One is the x-intercept and one is the y-intercept. Right? X-intercept is when y is equal to 0. Good. So e power x is equal to 0. That means x is equal to ln 0, which doesn't exist. So means you don't have a x-intercept. And to be honest, it makes sense, right? Think about any value of x which could actually give you 0. E to the power billion would be a very big number. E to the power negative billion, suppose, would be a very small number, but it'll still be a number. It won't be 0. Okay, I mean 0 is also a number, but e power negative billion will also have a value slightly greater than 0. Okay, so e power x will have no x-intercept. Now let's look at y-intercept. Y-intercept is when what is equal to 0? X equal to 0. So y is equal to e to the power 0. We should know that anything to the power 0 is equal to 1. So we have a y-intercept actually, which is 0, 1. Okay, not bad, Shamit. So cool, I can draw a graph. Okay, not bad. I drew decent lines. Okay, now what can we do? We just know 1 point. Okay, I know nothing else except 1 point. Well, we could do some we can get some intuitive idea on this. What happens if x is very large? E to the power something large, e to the power big, e to the power big. It's something big. Okay, like the literal definition of exponential growth, or like, you know, they say compound interest is the 8th wonder of the world. All that, the reason is, as your x gets bigger and bigger, your graph gets steeper and steeper. That's why with something like compound interest, they say, oh, as you invest for a longer and longer time, your investment money increases higher and higher and higher. That's the definition of exponential, basically. Think about it, okay? As x increases, y is increasing. And it's increasing faster and faster and faster and faster. So, could you agree that, okay, you have 0, 1 here. That's probably somewhere here, but this is 1. Okay, you have 0, 1. It's increasing faster and faster and faster. As x increases, y increases. And it increases at an increasing rate. So it looks something like this. As x increases, y increases. But y increases increasingly. Oh, what does that mean? What does that mean? It means, okay, x increases, y increases. But is the rate at which y increases positive or negative? It means that x is increasing, y is increasing. But is the rate at which y is increasing positive or negative? For example, for some of you who take physics, what's acceleration? The rate at which velocity is increasing, right? So suppose your acceleration is positive. It means as you move, your speed is increasing. But if your acceleration changes from 5 and it's slowing down to 3, it means your speed is increasing, but it's increasing in a decreasing manner. Like you're increasing because you're accelerating, right? But if it goes from 5 to 3, means instead of increasing 5 meters every second, now you're increasing only 3 meters every second. So that's what I mean by increasing decreasingly. And here it's increasing increasingly. So you could think of it as the acceleration is increasing. Okay? Now, what about the negative side of the graph? As x approaches a big value which is negative, like e to the power negative big, you can think about it. We should know from exponents that's equal to 1 over e to the power big. Okay? And we just discussed e to the power big is big. Okay? E to the power big is a big number. So 1 divided by a big number, it's a small number, right? So as x is becoming more and more negative, this e to the power big is becoming more and more big, so 1 over e to the power big is becoming smaller and smaller. Let's take an example, okay? Suppose x is equal to -1. -1. So you have e power -1, which is equal to 1 over e. Not bad. X equals to -2. -2, you have e power -2, which is 1 over e to the power 2. As x became more negative, it went from -1 to -2. E became e square. So 1 over e became 1 over e square. And what is larger? 1 over e square is larger, or 1 over e? 1 over e, right? So means as x goes more and more and more to the negative side, the graph becomes smaller and smaller and smaller and smaller. Okay, it becomes smaller and smaller. But here's a question. Okay, so it means it goes something like this, this, this. As x becomes more negative, it goes this, 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 this. Does it reach 0? Does it reach 0, Shraman? No, it doesn't. Huh? Why? Eventually it should, right? Well, think about it, okay? Let's say it's e to the power -billion. Okay? That's the same as 1 over e to the power billion. E to the power billion is an extremely large number. 1 over an extremely large number is an extremely small number, but an extremely small number is not equal to 0. So means it's becoming closer and closer and closer and closer and closer to 0. You can add the closer as many times as you would like, but it will still not reach 0. It will still not reach 0. So like that, but it still won't reach 0. Okay, let me just perfect the graph a bit. No, I don't have OCD, but the graph should look good, right? And this property that is getting closer and closer, but it's not reaching, is called an asymptote. Asymptote is a line which the graph never approaches. So in this case, the line is actually x equals to 0. The graph never approaches x equals to 0. So that's why x equals to 0 is called the asymptote. Very fancy name, I know, but you get the idea. Okay? So we know that this graph has an asymptote at x equals to 0. At a negative value, y is positive. Okay? But very little bit. It's like slightly greater than 0. Maybe 0.000001 greater than 0. Okay, but it's not 0. Okay, it's not 0. You can think about it this way. When your x is very negative, okay, when your x is very negative, you are almost squished to 0. Okay, filled with negativity, you are almost squished to 0. Your x is very negative, but you try so hard to remain positive. You never let yourself go down to 0. Your x is very negative, it's very negative, it makes you, feel even more closer and closer to 0 because your life is filled with negativity, but you are strong enough to make sure you never touch 0. Okay, that's one way you could think about it. And when your x is very positive, your life is filled with positivity, so you rise and shine over here. Okay, that's like a way you can think about it. Yeah, now let's talk about y is equal to ln x. Okay, let's find x-intercept, y-intercept. Y-intercept is when x equals to 0. By now you should know x cannot be 0. If you don't know this, slap your face, okay? X cannot be 0, which means there is no y-intercept. Argument cannot be 0. Okay, let's find the x-intercept. X-intercept is when y is equal to 0. That means ln x is equal to 0. X is equal to e to the power 0, so it's equal to 1. So 1, 0. Okay, that's fair. We have an x-intercept and we have no y-intercept. In exponential, we had a y-intercept but no x-intercept. You can see flipped, inverse. Inverse, okay? Now, okay, we know one point. Let's try to understand the shape of the graph. Let's use red this time. X, okay, that's not x, that's y, and x. Now, In this case, you think there'll be an asymptote. We know x can never be 0 and x can never be negative, so forget about this side. So I will cross this side out because x can just never be negative, right? So x can't be 0 either. So means x can be 0.0000000000001. X can be 0.00000000002. Okay, I could go so on. But x cannot be 0. That should make sense that it's an asymptote at y is equal to 0. Asymptote. It's called asymptote, but the asymptote is nice to say. So, and we know there's a point here. Now think about it, okay? As x increases, y will increase. You know, makes sense. But in this case, it's slightly different. Okay, we have an asymptote like this, y, and then y. That's how the graph will look. It will increase, but it will increase decreasingly. Okay, it's like your velocity is increasing, but your acceleration is decreasing. Okay, if you take physics, that should make sense to you. Your velocity is increasing, but your acceleration is decreasing. That's how this graph is like. Okay, and there's an asymptote at y is equal to 0. Okay, so that means that, you know, exponential equations have horizontal asymptotes and logarithmic equations have vertical asymptotes, and they'll be quite right. Let's actually see the relation which e power x and ln x have been plotted together. Okay, let's plot e to the power x and ln x together. Let me make the graph bigger. Okay, work with that. Okay, this is y, this is x. This graph will look like this. Okay, e power x, y is equal to e power x. Let me draw the ln x graph in blue. Okay, it looks something like this. Y is equal to ln x. Okay, and we know they are inverse functions of each other, don't we? So we know they are a reflection across y is equal to x, don't we? Okay, this is my best attempt to draw y is equal to x. Your y is equal to x also looks like ln x. My best attempt to draw it. Okay, so you could see that they, to some extent, look like a reflection. I mean, this point, we know this point is 0, 1, and this point is 1, 0. Well, yeah, that's a reflection. Here we have a horizontal asymptote. Here we have a vertical asymptote. Reflection, isn't it? So e power x and ln x are actually inverse functions of each other, which we already know, which also means they are a reflection. They are a reflection across y is equal to x. So what was the way we could think about it? This was the way, right? So when your x is very positive, okay, your life is filled with positivity. So your life, which is the red graph, e to the power x, when your life is filled with positivity and energy, you're very happy and your happiness is escalating increasingly. Okay, but when your x, I mean, okay, we can call her your x even if he or she is not your ex, but okay, very negative. Okay, your life is filled with negativity, which means that you will be crushing and crushing and crushing and crushing and crushing and crushing your life to 0. Okay, there's so much negativity in your life is sinking and sinking and sinking, but you're strong enough to hold on and not be 0. But the more negative your x is becoming, the more closer you're coming to 0, but you'll never be 0 because you're strong enough. Okay, so what you do is you get tired of being so close to 0. Okay, you change your x. Okay, you reverse your life, you inverse your life. Okay, so your life goes from the red graph to the blue graph. Okay, now you're a smarter person. You make sure to choose an x which is positive. Okay, you make sure to choose an x which is positive. So suppose you get an x which is just positive, okay, 0.00001. Okay, you'll be like, hiya, so much hard work for nothing. Okay, so you'll be very sad. So assume you go negative. Okay, but as your x comes more and more positive, you'll be like, okay, maybe all that was worth it. So eventually your life is also positive. You're very happy. Okay, but it's not escalating anymore. It's sort of like curved. Okay, it's your acceleration is decreasing in a way. Why? Because you learned a lesson from your previous x that you should not rely on them for too much happiness. Okay, so now a positive x makes you happy, but not completely. Okay, that's one way you could think about it. And another way you could think about it, y is equal to e power x. Okay, say e, okay, your teeth go like e, horizontal, right? Something like this, your teeth. Okay, it's shiny here. Okay, that's my best representation of your teeth. Okay, horizontal, right? So e power x have horizontal asymptotes like this. Okay, ln x, let's take ln. Look at this L over here. This L is a vertical line, right? So it has vertical asymptote. E power x, e, okay, it's a vertical line. So, okay, so ignore that message. Okay, e power x, e, it's a vertical line. Okay, so that means horizontal asymptote. Okay, ln x, L is a vertical line. Okay, e power x, e, so it's a horizontal asymptote like this. Okay, because your e horizontal, ln x, L is a vertical line, so it's a vertical asymptote, something like this. Okay, or you could think about it the x way, where your x is filled with positivity or negativity. Okay, this is a way for you to remember it. Or if you are just memorizing it the conventional way, then yes, you can glue it to your brain that exponential functions have horizontal asymptotes and logarithmic have vertical. Because we can't derive this every time in the exam, right? It'll be taking too much time. Okay, now let's go to a slightly more advanced functions like e power x and ln x are the standard functions, right? What about e power x plus 2 or 2 ln x minus 3? Let's go a bit more advanced. Okay, now suppose our graph instead now is 3e to the power x plus 5. Now, what do you think can happen? Firstly, let's see how the asymptote changes. Okay, we know that 3e power x also, like e power x, no matter what we do, 3e power x will never be negative. Okay, it will be a very small positive value like 0.00001. Okay, so it will never be negative. And now that asymptote was at x equals to 0. Now you're adding 5 to it. So it becomes x equals to 5, isn't it? So y is equal to 3e power x plus 5 will have an asymptote as x equals to 5 right now. So your graph is something like x equals to 5 is here, 5. Then your graph looks something like this. Here your x is negative, but you're not below 5 this time. Okay, e horizontal asymptote x equals to 5. What will this point be? Just have to make x equal to 0. So 3e to the power 0 plus 5 should be equal to 8. So this point is equal to 8. Okay, of course, this is y, this is x. Okay, suppose for logarithms, you have ln of 2x minus 5. We know that 2x minus 5 cannot be 0, it cannot be negative because argument should always be positive. So let's actually do one thing. Let's actually make it equal to 0 to see what value it cannot be. Okay, so it cannot be 5 over 2. And if at 5 over 2 it's 0, means below 5 over 2 it's definitely lesser than 0, right? So that means x has to be greater than 5 over 2. Or okay, if this doesn't make sense to you, 2x minus 5 should only be positive because argument can only be positive, so x must be greater than 5 over 2. It means 5 over 2 is our asymptote. So graph, okay, here is y, here is x. We have y is equal to 5 over 2 as our asymptote. Huh, just now you said x can't be, x is greater than 5 over 2? Oh yeah, sorry, x is equal to 5 over 2 is an asymptote. X is equal to 5 over 2 is an asymptote. And in the previous example, y is equal to 0, y is equal to 5 is an asymptote, okay? Now again, you probably like, oh, he's wrong, he's wrong, he's wrong. He doesn't know anything. Hiya. Simple mistake, you know. And if you caught that, that means you're understanding. Think of it that way. Okay, if you caught that means you're understanding. Okay, rest of the shape of the graph is the same. It'll look like this. Okay, how can you get the x-intercept? Y is equal to 0. So, okay, let's just do y is equal to ln 2x minus 5. So, ln 2x minus 5 is equal to 0. Can I sing? No, I cannot sing. So 2x minus 5 is equal to e power 0 is 1. So x is equal to 3. 3. Okay, x is equal to 3. This is how y is equal to ln 2x minus 5 looks like. Okay, here's how you can remember it, that whenever any logarithmic function you have, the argument should always be greater than 0. So what you could do is, to find the asymptote, do what I did here. 2x minus 5 can be greater than 0, or 2x minus 5 equals to 0. That way you can get the equation of the asymptote, but it's for you to judge on which side of the asymptote it will be. Okay? It's for you to judge on which side of the asymptote it will be. That's where this can come in. X is greater than 5 over 2 means it should be greater than the asymptote, means after the asymptote, means after 2.5. It means all positive values after 2.5, means all these values here and not these values here. Okay, and for exponential functions, it's always just going up, down, up, down, up, down. Okay, you have e to the power x, you have e to the power x plus 5. Okay, asymptote goes 5 up, minus 2, 2 down. Okay, so for exponential functions, the asymptote goes like this. Okay, for logarithmic function, it goes like okay, and that makes sense. You know, they are inverse functions of each other. So in one case, if y is equal to something is going up and down, in the other case, x equals to something will go left and right. Why? Because it's a reflection across y is equal to x. Simple, right? Okay, let's move on. Now, there's one more type of graph I want to talk about. So we know y is equal to e power x, right? This goes like ching, ching. Okay, wow, these are good lines I've drawn, touch wood. And then here. Okay, that's y is equal to e power x. Now, what about a graph which is y is equal to e power minus x? Okay, think about that for a moment. Pause the video, think. Okay, now I'm explaining. I hope you've paused and thought about it. If you haven't got an answer, keep thinking. Okay, keep thinking. This is not that hard. So y is equal to 1 over e power x. Let's try drawing that. Okay, lines are not as good as last time, but we can still manage. Tell me one thing, can e power x ever be 0? 1 over 0. Error, right? So e power x can't be 0. Means again asymptotic at 0 only. Okay, so asymptote y is equal to 0. Okay, I'm correcting myself. It's not x equals to 0. Y is equal to 0. Okay, now let's look at this graph. Let's see what happens when e power x is very, 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 very small. When is e power x very small? Somewhere here. Here, you want me to highlight? Somewhere here, e power x is very, very, very small. When x is at a very large negative value, e power x is at a very small positive value. When your x is very negative, you are almost to 0, but you try to remain as positive as you can. Okay? So, when x is at a negative value, y is at a value just greater than 0. So, 1 over e power x, if e power x is a value just greater than 0, means 1 over a very small number. Something like, okay, let's get back to the pen. 1 over 0.001. That'll be a big number. or 1 over 0.00001. Okay, I can't say too many zeros. It's like a tongue twister. Okay, get used to it. That'll be a very large number. So means here e power x is being a very small number, but 1 over e power x will be a very large number, maybe somewhere here, right? So actually, let's just draw that in a different highlighter. So 1 over e power x will be a very large number. And when e power x is a very large number, 1 divided by a very large number will be a very small number. So it will be something over here. And the intercept, you will notice, will just be the same. So the graph of y is equal to e power minus x. My guys, it looks something like, okay, that's bad. My dudes, let me try to draw it properly this time. It looks something like, okay, let me start from here. Maybe it's better. Where this is still 1 and this is asymptotic. Okay, if you are very, very, very sharp, you'll be like, hey, reflection across the y-axis. On point, man. It's a reflection across the y-axis. Okay, you don't need to know it's a reflection, but if it makes it easier for you to remember, then sure. Okay, you could think of it this way. X came from x to minus x. Okay, it went from x to minus x. So whenever, you don't need to know this, but maybe it helps you in your understanding. Whenever anything goes from fx to f of negative x, it's a reflection across the y-axis. And you might not be conscious of this, but you've actually probably used this many times in your life. And you've actually used this concept many times in your life. For example, oh, okay, sorry. Y is equal to x plus 5 looks something like, okay, it's lagging a bit. Don't worry. Okay, let me just draw it quickly. Y is equal to x plus 5 looks something like this. Y is equal to negative x plus 5 looks something like this. Reflection across the y-axis. Okay, so that could be one way you could remember it, that e power x and e power minus x, they're a reflection across each other across the y-axis. Now, of course, there's so many more combinations. For example, minus e power x minus e power negative x, or minus e power, yeah, I think that's it. Yeah, 4 combinations, and there could be 4 combinations for logarithms also. Okay, maybe not, because argument has to be positive, there's a restriction there, but there can be many combinations for logarithms also. Okay, so you could do things. Okay, either go to Desmos, okay, memorize all the combinations, okay, or the second thing could be use some logic to find the shape in the exam, or the third thing could be find many coordinates. Okay, for example, at x equals to 1, x equals to 2, x equals to 3, find many coordinates, plot it, and then that way you'll get a shape of the graph. You'll get a shape of the graph. Okay, so that's about some different types of functions you might be asked e power minus x. Okay, but generally, don't quote me on that, but generally they ask you the straightforward ones, e power x and ln x. Of course, there's e power x plus 5 or 3e power x minus 5. Okay, e power minus x minus e power x minus e power minus x, they're not so common, but they might ask you that, so be prepared also. Okay, another way you could think about it is that y is equal to e power x and y is equal to e power minus x, right? E power x, y is equal to e power minus x. For the same y value, you are having the negative x value, right? For the same y value, you are having the negative x value. So it should make sense that it's a reflection on the other side. It means it's a reflection across the y-axis. Okay, so that's another way you could think about it. But of course, you could also do all the other ways which I mentioned earlier. Now, there's one last thing I want to talk about, and that is the effect of this constant k on the asymptote. What's k? Suppose you have something like k e power x minus 3. Okay, let's give k a value like 3e power x minus 3. Okay, So does 3 affect the asymptote? Think about it. If it's e power x and 3e power x, sure, the steepness of the graph will be different. But do you think the asymptote will be affected? Suppose x is a large negative value again, so it's 1 over e power billion, suppose. That's very close to 0. This will just be, what? 3 over e to the power billion. This will also be a very small value. It will be almost equal to 0. But yes, now you might argue, yes, but this value is still greater. Yes, it's still greater. So means, suppose, let me do my best initiative. Suppose the black line is e power x. Suppose that a particular x value is over here. 3e power x will probably be somewhere here. It will be slightly higher. Okay, it will be slightly higher. Okay, I've drawn the graph slightly wrongly. Let me correct that. So 3e power x, yes, it will be slightly higher. It will still have the intercept at the same point. Its steepness will be different, but eventually both of them will still reach 0, right? So the asymptote is not affected by this constant k. Even for logarithmic functions, it's just the argument which has to be positive. If I do 3 ln x or just ln x, x must still be greater than 0. This 3 hasn't done anything. What's this 3 done? It's like a spectator, it's just watching. Okay. But it's not doing anything to the asymptote though. It's changing the graph. Yes, it's changing the graph. Okay? Not the asymptote. By the way, over here, if you haven't realized this red graph, there's still a bit of an inaccuracy because the coordinates won't be the same. Okay? The coordinates won't be the same. The coordinate over here will be 3. Okay? Not 1. The x coordinate here, dude. The y-intercept here will just be 1. But here it should be 3, yes or no? So that's why it looks something like this. Okay, are they parallel? That's a whole new discussion to have later, but that's not what we are concerned about right now. Okay, you could plot a graph in Desmos and check all that, but the point is that k does not affect the value of the asymptote. Okay, so we learned a bit more complicated graphs of logarithmic and exponential equations. Okay, we learned quite a nice way of remembering them. Okay, we learned that k does not impact the asymptote. We learned that there can be slightly different variations to the graph, like e power x, e power minus x, okay, or ln x minus ln x, okay, or ln negative x. Okay, there can be many variations for the graph, and we have to be aware of all of those. Yes, in a way, because they might ask us any of them, but many of the variations are rare. And we don't need to memorize all the variations, honestly. If any variation comes up, we can logically and intuitively find the shape of the graph. Or if we don't want to put so much brain into it, we could just plot a few, we could just find a few coordinates and know the overall shape of the graph and then sketch the graph, okay? But we need to show our basic workings, such as asymptote, finding the asymptote, finding the x-intercept and y-intercept if they have, and remember, exponential functions have a horizontal asymptote. You do e, okay, you have to go like horizontal asymptote. Logarithmic functions, they have a L is vertical, so they have a vertical asymptote. Okay, don't forget that, that's really important. And that's it for this session also. So our logarithm session is complete. Okay guys, that's it for this video as well. So that means that our logarithm one shot is complete. It was split into 2 parts because for logarithms is a huge chapter. Okay, it's one of the biggest chapters in Add Maths, so I had to split it into 2 parts. I hope you understood. I hope you can understand that. And let me know if you're interested for other chapters also. Okay, I did this chapter with logarithms, and if you all like it and if you all want other chapters also, then I will definitely do one-shot videos for other chapters also, in which the same way we break down each and every concept, okay, and we revise it all in one go or two goes if it's a pretty big chapter. Okay, I hope you enjoyed the video. That's it for now. Keep studying, keep enjoying. Bye.